let me kind of say it like this first. One, suppose I tell you that in this region of, well, let me start out. Let me go even further back. Suppose I tell you that in this region of space, there is a gravitational field G. This will be generated by what? By mass. Where?
Beneath it?
Given this picture, where would the mass have to be?
Beneath the arrows?
Underneath, right? Because objects with mass generate a gravitational field that points towards them. Since I drew this pointing down, the mass has to be down there. Like the Earth, for example. Now, okay, so what? The Earth generates a gravitational field. What if I take an object of mass m and I put it there? What is this gravitational field going to do to that object with mass m? Exert a force on it, called a gravitational force, right? And the gravitational force on that object will be the mass of the object that's experiencing the force multiplied by the gravitational field there where the object was placed. And since mass is a scalar quantity and gravitational field is a vector quantity, and mass is a scalar quantity that's always positive for anything, if it has mass, it's going to be a positive number. That means that the gravitational force has to point in the same direction as the gravitational field. So we draw the gravitational force like this. In the same direction as the gravitational field. That's exerting that force. What's really happening is that this gravitational field is generated by the Earth. And then you say that the Earth is exerting the force on this mass through the Earth's gravitational field. But we could just forget about the Earth and let's say there is a gravitational field there. It will be generated by the Earth. But we could just say there is a gravitational field there. And when this particle with mass is placed over there, it interacts with this gravitational field. Truly it's interacting with the Earth, but through the Earth's gravitational field. And then the Earth's gravitational field exerts a force on the particle of mass m, pointing, well, related by this. So since this is always a positive quantity, then the gravitational force always points in the same direction as the gravitational field that's exerting that force on this object. Number one. Number two. What if I tell you that just like over here, there was, by the way, it looks crooked, but they're supposed to be the same. What if I tell you that there is an electric field in this region? And the electric field is generated by?
Electric charge.
By objects with electric charge, right? So where would the charge be over here? Let's say, if the charge is over here, then what can you tell me about the charge that's producing that electric field? Positive, because it generates an electric field pointing away from it. But if the charge is over here, what can you tell me about the sign of this charge?
Negative.
Negative, because it generates an electric field towards it. Or we could have a combination of plus and minus, right? And but anyway, it's there. What happens if I now bring a charged particle, not the one that's generating this electric field, but just a charged particle, and I put it here? And the charge is Q. And let's make it positive. Then what will be the force on the charge exerted by this electric field?
E2.
Which truly is the force exerted by the charge, the other charge that's generating this electric field. So the expression is this, right? And now this is the electric force. And charge is a scalar quantity. So a scalar times a vector gives me a vector. But we have to be more careful than in the case of gravity. Because the mass of any object, if it has mass, is positive. Only positive. Never negative. I don't know of any object, we don't know of any object yet that has a negative mass. But charges, we do know of charges that are positively charged or negatively charged. Protons are positively charged, right? The nucleus of an atom is positively charged. Electrons are negatively charged. So if the charge is positive, then this force will have to be in the same direction as the electric field. That's actually the force. So the force will be this way, in the same direction as the electric field. But if the charge is negative, suppose I put another charge over here, right? And that charge is negative. If the charge is negative, then the force has to be in the opposite direction to the electric field. So the force has to be this way. Cool? So now comes this equation. Because this is not a gravitational force, this is not an electrical force, this is a magnetic force exerted by a magnetic field. So the issue is this. What if we have a magnetic field somewhere? Number 3. What if there's a magnetic field pointing this way? There's some moving charge somewhere that generates that magnetic field. Some moving charge, some current somewhere, maybe a solenoid, whatever, right? A toroid, whatever. There's some moving charge that generates this magnetic field. Now, what happens? So what good is it? Who cares? Well, you care if there's another charge in there that is now in the presence of this magnetic field. And what happens if this charge is here and the charge is Q? So this magnetic field can exert a force on this charge. And the force that the magnetic field exerts on this charge will be given by this expression. Now I'll say F magnetic equals Q V cross B. I like to call this gravitational field as exerting this force, I like to call it external. Because yes, this mass creates its own gravitational field, but in this expression here, this gravitational field is not the one generated by this mass, but by something else. So I like to call it external. So this is an external electric field, not generated by those charges Q, right? And you can call this external if you like to. See the point? Now, when you look at this expression, first of all, there's a lot that's said in this expression. This is the velocity of the charge Q when that charge is moving in this magnetic field. And it'll give rise to this force. So first of all, can you tell me, and you can discuss it with people, I'll give you some time. Can you tell me all the different scenarios where this force is going to be 0? I'll give you one. Can I give you one? Or no, you talk about it. How about you talk? I don't want to consider it.
What if not moving?
What are all the different possibilities? You know, you could say if the force is going to be 0, or if the force is going to be 0. Right? Let's consider all possible cases.
You're right.
When it's moving parallel with it, it's 0.
When there's no charge,
Oh, is that?
well,
Well, then that means there's nothing to move.
there's nothing there.
That's right, at least when it's moving.
Maybe it's a neutron. I don't know.
Oh yeah, that's true.
Don't have the time the charge is negative.
Then
It
it
would
goes
go
the other way,
opposite.
the opposite way.
That's a magnetic field acting on an electric charge. It's the same as an electric field.
Yeah, but this is a cross product.
Oh, you were supposed to be talking to everyone. Let's see, did anyone come in after I took attendance so I can mark you present?
I did.
So,
It is. It can be.
What do you guys say? Just
so Ara, who else? Jose?
Also,
Also,
moving parallel.
Can, right?
Because it's a cross product. So like
Sine of 0 is 0.
Oh, sure, right?
and sine
Can. Okay.
pi is 0.
Or 180.
Yeah.
Can when?
That's many one.
All right. Nicholas Newman?
I'm assuming the S is to think of it as a trunk.
Oh, okay.
There's no magnetic field. There's no charge.
Oh, yeah.
When it's not moving.
Daisy, right?
That's what I'm saying. There's no force of gravity, there's no mass.
And the last name?
But like, you can leave the magnetic field, you know, so like,
I guess. I don't think.
Hmm.
Like, isn't. I wonder. If the isn't it moving the charge? It's like moving the charge.
and
does
core?
Also create its own
Yeah.
magnetic field. This is probably not that, because it's a moving charge.
So,
That's probably one
Does it
of the
create
include
it?
Scott is not here.
Yeah.
Aiden Murphy is not here. Paul or Paul is
Wrong
here?
message.
Okay.
He came to lab last week.
So-
but I didn't show up. Right? Yeah. He didn't show up to class then. Or he came.
So, what are all the different scenarios when there's not gonna be a magnetic force?
When it's moving.
One. Let's count them. I mean, what I'm trying to do is, you see a formula like that, and it's like, it's really talking to you. It's telling you information, right? So what is it telling you, as opposed to just memorizing it? Right? So what is it saying? So F magnetic equals 0 if, or, when what, if what?
The velocity of the particle is parallel to the magnetic field.
Right, because if the velocity if the particle is moving this way, then the cross product of the velocity vector with the magnetic field will be 0, right? So if the charged particle is moving in the same direction as B. What else?
If it's moving opposite.
If it moves in the opposite direction, what happens if the particle has a velocity in the opposite direction? So if the charged particle is moving in the opposite direction of the B field. So if a charged particle moves in the same direction as the magnetic field, or in the opposite direction as the magnetic field, charged particle is not going to feel anything. It's like you don't exist. I could care less for your existence because you ain't doing anything to me. What else?
When it's not moving. When velocity is
Right,
0.
right. What happens if the charged particle is at rest? If it isn't moving, magnetic field is not going to do anything to it. Anything else?
If there is no magnetic field.
If there is a magnetic field, what happens if there's a charged particle moving in space, but there's no magnetic field there? So, if it doesn't exist, it's not going to do anything, right? What else?
If it's a neutral charge, or the charge is 0.
Right. What happens if you have a magnetic field, but then the particle that's moving is a neutron, which doesn't have an electric charge? So the particle has to be electrically charged. It has to have an electric charge. So, in one sentence, when is the magnetic force equal to 0? When a particle is not charged, or is not moving, but is charged, but is not moving, or if it moves in the same or opposite direction as the magnetic field, or if it moves in a region of space where there is no magnetic field. Right? So, but what happens if the particle is charged? It is not moving in the same or opposite direction to the magnetic field, and it is moving in a magnetic field region. Suppose the velocity is this way. What will be the direction of the magnetic field? Therefore, in this case, it doesn't satisfy any of these conditions, so there will be a magnetic force. First of all, which way would it be pointing?
Out of, or either out of or into the board because it has to be perpendicular to both.
Right? So, finish the calculation. Which way is it going to be out of those two? Right hand.
Into the board? Or wait. Yeah, into the board?
Which one?
Into the board, I think.
Yeah.
He's asking again, I think I'm wrong.
So, first vector, that's your four fingers. So your four fingers have to point that way. And the magnetic field is to the right. Your palm is to the right.
Yeah. So into the board. Right?
If what?
If it's positively charged.
Exactly. This cross product is into the board. That doesn't mean that this force is going to be into the board. We have a scalar. When we do V cross B, that's a vector. So we have a scalar quantity, the charge multiplied by the vector to give me a vector. So this force will be in the same direction as the cross product only if the charge is positive, like a proton or the nucleus of an atom. But what happens if the charge is an electron? Then the velocity of the electron is that way, so V cross B is into the board, right? So this vector, this is V cross B, this is into the board, but if this is negative, the force is going to be out of the board, in the opposite direction of into the board. Yes? So when solving a problem, quiz, test, homework, right? And they ask you, what is the direction of the magnetic force on this charged particle that moves in this magnetic field? Pay attention to whether the charged particle is positive or negative. If the charged particle is positive, then the force exerted by the magnetic field will be in the opposite direction of this cross product. But if the charged particle is positive, no, did I say positive? If it's positive, I saw a minus sign, but if the charged particle is positive, then the magnetic force acting on it will be in the same direction as this cross product. But if the charged particle is negative, then the magnetic force acting on the negatively charged particle will be in the opposite direction to this cross product. Yes? Let me see if I can go get something. I'll be right back.